7.2 Linear Transformations. We will be talking about the equivalence of 2.7 and 2.8 for vector spaces. V and W are vector spaces. A mapping T from V to W is called a linear transformation, or simply linear, if for all U and V vectors in V and all scalars C, the image of the sum U plus V is the sum of the images TU plus TV, and the image of the scalar multiple is the scalar multiple of the image. This definition is very much like what we have in Chapter 2. V is the domain of T and W is the codomain of T. Like before, we define linear operator. A linear transformation from a vector space V to the same vector space V is called a linear operator on V. Consider C infinity, the subset of f of R, that consists of functions that have derivatives of all orders, and D, a mapping from C infinity to C infinity, so it's actually a linear operator on C infinity, and it's defined like this. D of f is equal to f prime, the derivative of f, for all f in C is C infinity. The question is D a linear operator? If we want to show it's a linear operator, then we need to show it preserves vector addition and it preserved scalar multiplication. So we need to show if the derivative of f plus g is the same as the sum of derivative of f and derivative of g. So f plus g, derivative of f plus g, the same as derivative of f plus g, derivative of g, and that's the same as d of f plus d of g, so the first property is satisfied. Now, scalar multiplication, d of cf, that will be the derivative of cf, and that's the same as this one, and the same as c d of f, so again, the second property is satisfied. So we can conclude D is a linear operator on C infinity. Theorem 7.4 has some properties of a linear transformation, and these properties are very much like what we had before in Chapter 2. V and W are vector spaces. T is a mapping from V to W, it's a linear. And for all UV in the vector space V and all scalars A and B, the following are true. The image of T is the zero vector in W, and the image of additive inverse of U is the additive inverse of image of TU, of image of U. And the image of U minus V is equal to the image of U minus the image of V. And the image of the linear combination is the same as the linear combination of the images TU, TV. The proof is very similar to what we have in Chapter 2, so we will omit the proof here. Let's consider an example. T is a mapping from P2 to R3, and P2, as we recall, is the collection of polynomials with a degree less or equal to 2. T of f of x is like so. It's a 3 by 1 vector because this is the codomain is R3. And the first entry is f of 0. The second f prime of 0 and the third f double prime of 0. So this one is the value of the derivative of f evaluated at x equal to 0. And this is the value of f double prime at x equal to 0. Would this mapping be linear? Well, we know f of x is a polynomial in P2, so let's write it as a plus bx plus cx squared. Then f prime of x will be bx plus... f prime of x is b plus 2cx, and f double prime of x is 2c. So f of 0 is simply a, and f prime of 0 is b, and f double prime of 0 is 2c. And we can indeed verify that such a mapping preserves vector addition and scalar multiplication, and so it's a linear transformation. Some definitions about linear transformations, very similar to what we had in Chapter 2. V and W are vector spaces. T is a mapping from V to W. It is linear. And the null space of T is the collection of vectors in V such that the image is the zero vector in W. The range of T is the set of all images of T. So it's the collection of all images. And we say T is onto if the range of T is the same as W. And we say T is 1-to-1 if distinct vectors in V have distinct images. All these definitions are just like what we had in Chapter 2. For example, let's consider the mapping U from M by N to M by M. As defined by U of A is equal to A transpose for all matrices A in MN. And let's find, and we would like to find the null space and range of U. What will be the null space? The null space is the collection of vectors whose images is the zero vector. And in this case, that will be the zero matrix. And U of A is the zero matrix if and only if A is the zero matrix itself, M by N matrix, M by N zero matrix. And the null space is simply the zero matrix. How about the range? The range of U should be all M by M matrices. So it's M in M. Is this U onto? That's indeed onto, right? Because it's the same as M in M. Another example, let's consider the linear transformation from P2 to R3 that we have seen earlier, the example. And then if f of x is a plus bx plus cx squared, the image of f of x is simply ab and 2c. And we know this is a linear transformation. Would the linear transformation be 1-to-1 and onto? Well, we can consider its null space, right? What would be the null space of T? If this vector is a zero vector, that means in particular this f of x is the zero polynomial. So null space has only one vector. It's the zero polynomial. So indeed, this T is 1-to-1. How about onto? This is 1-to-1. We look at the image. And this can be an arbitrary vector in R3, right? So the range is R3, and this is onto. And the result, very similar to what we had in Chapter 2, is that V will be vector spaces, T from V to W is linear, T is 1 to 1 if and only if the null space of T consists of only the 0 vector. Now we can go back to this example and ask if U is 1 to 1. And we see that the null space has only the 0 matrix. So indeed, it's 1 to 1. A definition. V and W are vector spaces. T is a linear transformation from V to W. And we say T is an isomorphism. And we will abbreviate it as iso if T is both 1 to 1 and onto. So if it's 1 to 1 and onto, then we say it's an isomorphism. In this case, we say V is isomorphic to W. And isomorphic actually means structurally identical. So that it actually says that V and W have the same structure. In Greek, this word means the same, and then this word means shape. So this word isomorphism itself, it means same shape. That means that V and W are of the same shape. We will get more sense out of this isomorphism later. Remember in chapter 2, when we have a linear transformation that is both 1 to 1 and onto, then the linear transformation is invertible and its standard matrix is invertible. Right now, with vector spaces, we don't have a standard matrix to work with, but we can still consider invertibility of T in this case. V and W are vector spaces, and T is a linear, and it's an isomorphism from V to W. A question. In this case, T is an isomorphism case. For all vector in W, can we find an unique vector V such that W is the image of V? So here T is a mapping from V to W, and we already have a vector W here, and we would like to know if we can find a vector V here so that W is the image of V. And we know we can do that because T is onto. It's isomorphism, so it's onto. So any vector in W is the image of a certain vector in V. So we can find V such that W is the image of the vector V. And would such a V be unique? We are asking uniqueness as well, right? Is such a V unique? And surely it is, because T is isomorphism, so it's 1 to 1. So this V is unique. Alright, so for any vector in W, we can find a unique V such that it's the image of this V. So let's define this. This T inverse function is from W to V, and this T inverse of W is equal to V. And what is this V? This V is the vector such that W is the image of V. Okay, because we know for any vector W here, there's a unique vector in V so that W is the image of that vector. So we seek out this vector, and this is the image of W under T inverse, this V vector. This unique V vector here, we defined it as the image of W under T inverse. And this T inverse is called the inverse of T. An isomorphism is a linear transformation that has an inverse. And so isomorphism is also called an invertible linear transformation. Theorem 7.6 says if T is a linear transformation from vector space V to vector space W, and T is an isomorphism, then T inverse, which we had just defined, from W to V is linear and is also an isomorphism. Let's first show it's linear. Suppose the image of W1 is V1 under T inverse, and the image of W2 is V2 under T inverse. Then we need to show that the image of this linear combination is the linear combination of the images. Well, we don't know if T inverse is linear or not yet, but we know T is linear. So T, the image of this linear combination, is the linear combination of the images TV1 and TV2. And this is the same as alpha V1, alpha V2. Alpha W1 plus beta W2. From this relation, we know the image of this vector under T inverse would be this vector. So the image of alpha W1 plus beta W2 would be alpha V1 plus beta V2. And that's the same as this plus this. And that's what we start off to show. Now let's show that this T inverse function mapping is 1-to-1 and it's onto, and hence it's an isomorphism. First, let's show it's onto. If we want to show it's onto, then we need to show that for any V in W, we can find a W vector in W such that the image of W is equal to V. Every vector in V is an image. That's what we need to show. So for every vector V in V, let's call W to be the image of V. Then the image of W under T inverse will be equal to V. So this V is indeed the image, an image vector. So T inverse is indeed onto. Now let's show 1-to-1. 1-to-1 means that if two vectors have the same images, then these must be the same vector. So let's say W1 and W2 have the same image, equal to V. So this is the image of W1 minus W2 under T inverse is 0 vector. The image of this W1 minus W2 vector is the 0 vector. And this means in particular that the image of the 0 vector under T is W1 minus W2. But we know T is linear, right? So the image of the 0 vector is the 0 vector. And therefore, W1 and W2 are the same vectors. A question. Suppose we have V, that V is isomorphic to W. Is W isomorphic to V? When we say V is isomorphic to W, what this means is we can find an isomorphism that's both 1-to-1 and onto we can find an isomorphism from V to W, then V is isomorphic to W. So there is an isomorphism from V to W. Now the question is W isomorphic to V? That means, can we find an isomorphism from W to V? And surely we can, because T inverse is linear and also an isomorphism. If V is isomorphic to W, we can find an isomorphism from V to W. And the inverse of that isomorphism, T inverse, would be an isomorphism from W to V. So W is isomorphic to V. So if V is isomorphic to W, W is isomorphic to V. And we simply say V and W are isomorphic. The question, are P2 and R3 isomorphic? That means, can we find an isomorphism from P2 to R3? We have an isomorphism, an example of isomorphism already, don't we? This T from P2 to R3, it's both 1 to 1 and on 2, so it's an isomorphism. So P2 and R3 are isomorphic. These two are isomorphic vector spaces. Now let's consider composition of linear transformations. VWZ are vector spaces. T is a linear transformation from V to W. U is a linear transformation from W to Z. The composition UT is from V to Z is defined like this. UT of V is U of T of V. Theorem 7.7 says that the composition of two linear transformation, U, T, U are both linear, the composition of two linear transformation is also linear. And the proof is very similar to what we have in chapter 2. An example, T is from P2 to R3. Well, this is the example that we had earlier. And U is from R3 to M2 by 2. This is U of a vector STU. Then the image is a matrix in M2 by 2. It's STT, both TT and the off-diagonal term, and then U here. Now let's consider the image of this polynomial under the composition mapping UT. This is the same as U of AB2C, because T of this polynomial is equal to AB2C, as we have derived earlier. By definition of U, this would be A and B, B, and 2C. It can be further shown that if both TU are isomorphism, both of them are isomorphism, then their composition is also an isomorphism.